Hey everybody, welcome back. This is chapter 4, and we're talking this time about isotopes, which is when the number of neutrons in atoms of the same element varies. So let's first start by defining what an isotope is. So atoms that differ only in the number of neutrons present are what we call isotopes. So recall that the number of protons is what determines the identity of an atom. So atoms that have the same number of protons, but just a different number of neutrons, are called isotopes. They're isotopes of the same element because all the isotopes have the same number of protons. They have the same element identity. When we write the symbols for isotopes, the mass number is always included because for isotopes, the difference between different isotopes is the number of neutrons. And the chemical symbol that includes some reference to the number of neutrons is the chemical symbol that includes the mass number, because as shown down here, the mass number is the number of protons plus the number of neutrons. So for isotopes of the same element, the number of protons is always the same because it's the same element, but the number of neutrons is what varies. So the mass numbers for different isotopes of the same element will be different. They're all the same elements. They're going to have the same number of protons. It's just the number of neutrons that's changing. So there's two ways to write chemical symbols that include the mass number. The first way is to write the chemical symbol. And then above and to the left, you include the mass number. Mass number is number of protons plus the number of neutrons. And then down below to the left, you include the atomic number, and that's just the number of protons. So for example, for something like neon 20, you'd write neon. Its mass number is 20. And by definition, if you check the atomic number for neon, it always has 10 protons. The other way to write chemical symbols that include the mass number is to write the chemical symbol or name first, and then a dash, and then the mass number. So for neon 20, we could write Ne20 or neon 20. So again, the mass numbers are always shown because when we're dealing with isotopes, we're really interested in how the neutrons vary, because isotopes of the same element are all going to have the same number of protons. We can always look up the number of protons based on the identity of the element. Neon always has 10 protons, but in isotopes of neon, the number of neutrons can vary. So in neon, there's naturally 3 occurring isotopes. That means that if we take a whole sample of neon atoms, and we figure out of that whole sample of neon atoms, how many are neon 20, how many are neon 21, and how many are neon 22, we can figure out what's called the natural abundances of those isotopes. So all elements have their own kind of unique natural abundances. For neon, neon 20 makes up 90.48% of all the neon atoms out there. Neon 20, which means there's 10 protons plus 10 neutrons in the nucleus of a neon 20 atom. Neon 22 makes up 9.25% of all the neon atoms out there. So this is neon 22. It's still neon, so it still has 10 protons, but now the mass number is 22, so that means it must have 12 neutrons. 12 plus 10 makes 22. And the lowest abundant isotope of neon is neon 21. Neon 21 makes up less than 1% of all the neon atoms out there. Neon 21 is still going to have 10 protons because it's still the element neon. And now it has 11 neutrons. 10 plus 11 add up to 21. So for isotopes, the chemical properties are all similar for isotopes of the same element, right? We're dealing with neon in each of these isotopes. So the identity of the element hasn't changed. The electron arrangement is also the same. So that leads to the chemical properties being similar for elements, for isotopes of the same element. What does change is the masses. Because each isotope has a different number of neutrons, neutrons contribute to the mass of an atom, so the masses of the different isotopes can vary. We check out neon in a little bit more detail. This is a summary of what we just talked about. There's 3 ways to write the chemical symbol for the neon isotopes. Neon 20, neon 21, and neon 22. You can use either notation. because they're all neon, they all have the same number of protons, but it's the number of neutrons that varies. So these are 3 isotopes of the same element, 3 isotopes of neon. To figure out the mass number, you add up the number of protons plus the number of neutrons equals the mass number. If you're given just the mass number, like in this example here, we have neon 20, and you want to find the number of neutrons, the number of neutrons is going to be the mass number, in our example 20, minus the number of protons, 10 because it's neon, gives 10 neutrons. So given the mass number, you can always calculate the number of neutrons, or if you're given the number of protons and neutrons, you can always calculate the mass number. And then the percent natural abundance. This tells us of taking like a collection of naturally occurring neon atoms, what percentage of them are going to be neon 20, what percentage of them will be neon 21, and what percentage of them will be neon 22. And this is important when we start talking about how to calculate the atomic mass of the elements, because when we're working with, say, neon or carbon or any element, we don't get to like pick atom by atom what isotope we want to work with. We're just working with a collection of those atoms. And so to come to a calculation of the atomic mass of, say, neon, which is what's listed on the periodic table, we have to take into account that most of the neon atoms have 10 protons and 10 neutrons, but some of them are a little bit heavier. And so we use these percent natural abundances along with the masses of each of these isotopes to calculate kind of the average overall mass of a collection of neon atoms. And that's how we arrive at what's called atomic mass or atomic weight, which is the last section of chapter 4. So carbon has 3 naturally occurring isotopes, carbon-12, carbon-13, and carbon-14. Carbon-12 has 6 protons and 6 neutrons. It makes up 98.89% of all the carbon atoms. Carbon-13 has 6 protons and 7 neutrons. 6 plus 7 equals 13. Makes up just over 1% of all the naturally occurring carbon. And carbon-14 has 6 protons and 8 neutrons. And this one is unstable. There's basically too many neutrons shoved inside this carbon nucleus, so it's unstable. It wants to get rid of some of that mass inside that nucleus. And so every about 5,730 years, half of the carbon-14 decays or turns into nitrogen atoms. Basically, a neutron turns into a proton and you get nitrogen. So because this is happening kind of constantly with carbon-14, and because all animals are ingesting carbon, we have this kind of steady rate state amount, this is stable, of carbon-12 in our bodies and in our bones. So archaeologists and people interested in finding out the ages of things can take the amount of carbon-12 over time, and that's going to be about constant because it's stable. So however much carbon-12 you have in your bones, or an animal has in its bones when it passes away, it's going to stay stable. It's going to have that amount even, 1,000 years later. But carbon-14, because it's unstable, carbon-14 is going to slowly decay over time. And by looking at the difference between carbon-12 and carbon-14, scientists and archaeologists and biologists can come up with how old something is. How long ago did the carbon-14 start decaying without being replaced by the animal continuing to eat? So this is the basis for what's called carbon dating. It's used to figure out the ages of things that have died a long time ago. So we're going to watch a quick video on that goes into a little bit more detail to learn about one of the really cool applications of isotopes.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
Okay, so that was one example of an application of isotopes. Isotopes are also used in radiomedicine, as well as generating nuclear energy and creating nuclear weapons. So radioactive isotopes are isotopes that are highly unstable. And they're likely to decay. They're so unstable, they have typically too many things crammed inside their nucleus that they're going to decay into something else, to a more stable state. And when they decay, they're going to release some energy from that process. And so in nuclear medicine, we use this with isotopes that decay in such a way that they don't harm the body to do things like diagnostic imaging with CT and PET scans. These radioisotopes used for these types of scans, they decay, but their decay products don't harm the human body. And so we can use this to image different parts of the body with very high specificity. Radioactive isotopes are also used in radiation therapy for cancer treatments. In this case, doctors implant a very small quantity of radioactive isotope that when it decays, it's going to emit a high energy particle that kills the cells around it. And they do this on purpose, very specifically at specific locations in the body to kill cancer cells. So that's like radiation therapy or nuclear therapy. Radioactive isotopes, like isotopes of uranium, are also used to generate energy and to make weapons. So when radioactive isotopes decay, oftentimes a large amount of energy is released as part of that decay process. When you're changing what happens inside the nucleus, the number of protons, the number of neutrons, a lot of energy is involved in that. And so a lot of energy can be released. If we harness the energy, we can convert it into a relatively clean source of power. If we don't harness it and we let it kind of go out of control, then that's where nuclear weapons come from. So let's do a practice problem. Let's determine the number of protons, neutrons, and electrons for the following isotopes. We did a problem similar to this earlier in the lectures, and we were looking at chemical symbols and understanding what they mean. So this might be a little bit of review for you. Okay, so we want to determine the number of protons. So for iodine 131, the number of protons is based on the identity of the element. So iodine is atomic number 53. So it's always going to have 53 protons. Now to determine the number of neutrons, we can use the mass number. So we have iodine 131. So our number of neutrons is going to be 131 minus 53, the number of protons, to give us the number of neutrons in iodine 131. Let me just pull out my calculator quick so I don't mess up that math in my head. 131 minus 53 gives us 78. And then the number of electrons, this is a neutral atom, so the number of protons and electrons will be equal. We do the next one, potassium 40. Potassium, by definition, always has 19 protons. So if we have a mass number of 40, and of those atomic particles, protons and neutrons, 19 of them are protons, then 40 minus 19 will give us the number of neutrons. So we have 21 neutrons. And because this is a neutral atom of potassium, the number of electrons and protons is equal. So 19 electrons. We have mercury 201. So by definition, mercury has 80 protons. So we take 201, its mass number, minus the number of protons to give us the number of neutrons. 201 minus 80 gives us 121 neutrons. And this is a neutral atom of mercury, so the number of protons and electrons is going to be equal. And last one, we have fluorine 19. So all fluorine atoms have 9 protons by definition. So to figure out the number of neutrons, we take the atomic number, the mass number minus 9 gives us 10 neutrons. And this is a neutral atom of fluorine. There's no charge listed, so it must have 9 electrons as well. Okay, our last section of chapter 4 is what we'll do next. It's going to be on atomic mass. We calculate the atomic mass of the elements as the average mass of an element's isotopes. I'll see you then. Thanks.